All right.
Okay, so I'm going to be talking about a kind of a slightly different space and a particular solution we came up with for a problem. First, I want to mention this is work supported by the U.S. Census Bureau. However, as noted before, it does not represent a statement by the U.S. Census Bureau. This is purely our own as independent researchers. Myself, Sean Merrill, who's a graduate student at Purdue. Keith Merrill is faculty at Brandeis, along with Eric Hansen, who's a student there. We have been working with the American Community Survey, which introduces a different set of challenges from decennial. So the American Community Survey is much higher dimensionality, order of 250 attributes being collected. It's also a sample of the population, which it gets rid of some of these constraint problems we have, but unfortunately not all of them. And starting out with the current processing approach introduces some additional challenges. So some things we've run into: missing data imputation. A lot of these things aren't filled in, and we'll get into what this means in a bit. That's the one we're going to be concentrating on today. Some other things that come up: it's a stratified sample, it's not a random sample.
Yes, it is.
What?
Stratified sample is a random sample.
Well, okay, it's not a uniform random sample. It's not a simple.
Multi-stage probability sample.
Yeah, that's truly, it actually gets into it. So one of the things is they do some weighting of the sample to conform to known ground truth values. This throws some real wrenches into the works. But we're just going to concentrate today on this first one, which is missing data imputation. So does this really impact privacy? Well, if we think about it, suppose we have a situation like this and we impute missing data by looking at characteristics of similar individuals. Now, there's a couple ways missing data is imputed. One is known characteristics. If you don't answer citizenship, but you say you were born in the US, they can take a pretty good guess that you're a US citizen. But other times they can't do that, and so currently what they will do is impute this missing data from people who are similar. So we have kind of the dotted individual, maybe filled in from someone, whereas the dashed from someone similar to that. And assuming those rules, if we said dashed individuals are blue, dotted individuals are brown, this really doesn't impact sensitivity. Where we come up with those rules, again, could, but we'll assume it doesn't. But this allocation problem is different. We go to a neighbor and we say, because you're similar to the neighbor, this increases sensitivity. Because if we change the color of one of those neighbors, it now changes two individuals. Or potentially more individuals if we have a situation like this. Again, not likely, we hope. We hope we're not going to end up with most of the data being missing. But if you just start with a simple global sensitivity, you can construct a situation where you get a dramatic change. So we want to avoid this. You can see, remove one individual from the data set, everything changes. So one idea, let's just say, let's not reuse a donor. Once someone has been responsible for allocation, they aren't responsible, they aren't used again. Interestingly enough, the existing census allocation problem does something similar to this. And we thought, okay, wouldn't that be nice? Turns out it's not quite that nice. I mean, you can see right here we get a very simple situation where we get this sort of an imputation. So let's say our query is the number of blue squares. We see there's 4 blue squares that we've imputed from the data. Now let's take our neighboring database by removing that circle. We redo our imputation, removing each item after we've done the imputation from left to right here. And what's happened? Even though we're only using each individual once, we get this weird situation where our sensitivity is actually very high.
Could you explain the graphic?
So the graphic, the idea is my neighboring database, I removed one individual. And now I impute this unknown, this missing data, by going to the nearest neighbor, which is now this one instead of the one that I removed. So I impute that value. Now I say, I don't want to reuse somebody because that kind of sends my sensitivity off through the roof. So I'm going to remove this one from doing the imputation. This needs to be imputed. This is now the nearest available donor. This is the nearest available donor. This is the nearest available donor. So using this simple idea that I'm going to only use a donor once doesn't actually help my sensitivity. So, you know, it was kind of our initial thought was, hey, there's this nice thing. Maybe this will help us out. No, it didn't. You know, so we have something where we can say, well, global sensitivity is high. Using this a simple approach, even our local sensitivity is high. So, you know, one solution would be, say, you're just going to ignore your missing data. You compute your statistics without the missing data. This would give us kind of our lowest variance with respect to it. We're not basically you know, increasing the amount of noise we add based on this imputation. The problem with this is it potentially biases the result. You know, is the data missing uniformly at random? History suggests that that's not the case, that when someone doesn't provide an answer to a question, that there tends to be some correlation with other factors, and we can end up asking queries where we end up with a biased result. Hard to measure. Hard to really know that because the answer, the data we would need to answer this is missing. But people do some studies to try to evaluate this. We can compare it with other things like what a similar query would be on the decennial census to get some idea of these things. So, you know, what we would like to do is, you know, if we've got something like this where there is quite a bit of bias, what we'd like to have is what's a low sensitivity allocation method. We can still keep this as an approach to reducing the bias and yet not have the problem of this very high sensitivity. So what we went with is, can we do something where we can use smooth sensitivity? We know our global's high. We know using this simple approach didn't work, but can we come up with an approach that allows us to get smooth sensitivity? So what we did is a similar idea. We're going to go back to the nearest neighbor, but not try imposing this constraint that you only use something once. What we really need is the idea that a local change really is local. So if I'm imputing to the nearest neighbor by taking the value from the nearest neighbor, removing that value would only change the nearest neighbor. It's not going to change things elsewhere. It keeps the changes localized. The straight nearest neighbor will do this for us. And what we find is, typically each donor is closest to few donees. In fact, looking at the ACS public use MyScro data set, most cases, someone with a missing value, there's an exact match on many criteria with someone else in the data set, at least on the attributes they're currently using to do this allocation. And the kind of highest exact match donee to donor ratio, or kind of a lower bound on our local sensitivity, is around 4. So this suggests that smooth sensitivity could work. Yeah, there's still a lot to be worked out to see what it means. So what's the idea behind smooth sensitivity? The basic idea is that the neighbors of the current database don't induce big changes. That getting really high sensitivity situations, you have to get a long ways away from your start. And so the idea is for some beta greater than 0, the beta smooth sensitivity is defined in terms of the local sensitivity and the distance. And it's the maximum of your local sensitivity as you go farther away, but as you go farther away, you get to reduce that impact by this multiplier. So intuitively, as we get farther away, our local sensitivity may go higher, but our smooth sensitivity hopefully goes down. Assuming this number is large enough relative to this increase, or decreases rapidly enough relative to this increase, we're able to get this reduction. And kind of the key result out of the Nissim, Radikova, and Smith work is that this gives us epsilon differential privacy. Actually, they also worked out an epsilon delta version. We came up with some of the same things that Dan was coming up with, which is when we looked into this, it turned out that the epsilon delta really didn't help us, that their straight epsilon version was actually giving us nicer results in a somewhat different way. And again, why this is happening, something we didn't get deeply into. The fact that we seem to be getting better results with the straight epsilon made us happy, or the epsilon 0 made us happy anyway, because then we don't have to worry about all of the additional explanation of policy. So we'll get back to this when we look into how this works in our specific problem.
By epsilon 0 version, you mean the one with the Cauchy? Or what do you mean?
In terms of the epsilon 0, or straight epsilon differential privacy.
Which noise?
Which noise? We'll get back into that and go into, but it is the Cauchy that you're talking about. There's a couple of little tweaks we did to get it to work well for this particular problem, but it builds heavily on this, on the same idea. So what we did is said, okay, let's abstract this problem to just a straight nearest neighbor. And actually, while we're going to talk about it in terms of the one nearest neighbor, it extends to k nearest neighbor for a variety of functions of how you combine the k nearest neighbors. Straightforward extension. So what we want is, initially we're thinking, okay, an upper bound on the smooth sensitivity of the function of some query on the data and the allocated values. And like I say, we're going to just show this for count queries. You're counting some subset, the number of blue squares type of example, over your data allocated with one nearest neighbor. So to start this out, what do we mean here in terms of sensitivity? The idea is kind of the Donee change, which is the impact on your count query between two data sets. So the change between those data sets is equal to the original data set and then the change union, the set size that changes. So it's basically the number of Donees that have changed based on the donor that changes, or the donor changes between these two data sets. Now, as you go farther away, you get more donors that could change, potentially. But basically the idea is the number of incomplete tuples that have changed as you transform the data set. And what we're able to show is certain things that will happen on this. I somehow got a character in there that doesn't belong. That G is my hitting the keyboard randomly. So basically at a certain distance, the sensitivity at that distance of D is less than or equal to, or is less than the sensitivity at a larger distance. And in particular, we can bound this by the distance times the local sensitivity. This is kind of a key statement, but the idea here is that if you can get a large change based on one donor at some future point, you can set up the problem in a way such that you can get a fairly large change now.
So
Yes. Yeah.
is this a property of the nearest neighbor?
It's a property of the nearest neighbor. These are specifically properties of the nearest neighbor. And this allows us essentially to work out that our donor change or that as we change the donors, we can get an upper bound on how big this change is going to be by looking at our local sensitivity. As this means we don't actually have to calculate this exponential number of sensitivities as we go away. Now, the trick is, in order to get that, the differential privacy, we need this to be a smooth upper bound. The idea in smooth sensitivity, this needs to be a smooth upper bound. And, okay, so what we've gone here is just getting us an upper bound, not necessarily smooth. But the idea is that we can say that our local sensitivity at some distance is bounded by our current local sensitivity. And that means that we can come up with these bounds on the local sensitivity at any given distance as we go farther and farther away from our current data set. So we have these bounds, and now what we need to get to is this idea of a smooth upper bound. And so now what we're essentially saying is that we want to take the maximum distance over these changes and the sensitivity kind of before we make that change, the previous step. And this is where it starts getting to be a little bit tricky. And in fact, if you look at smooth sensitivity, the original paper worked out some beautiful examples, and then there's been not a huge number that have been worked out since then, because it does turn out to be a difficult thing to get. Our first idea was, hey, can we just do a greedy algorithm which gets us several steps out? Can we say that our maximum change is based, that if each step we find the maximum change, will that extend going out? It turns out it's not that simple. So here's an example where we can see, in this case, we're imputing locally, but if we put a donor, here, it imputes on all these. We get these 4. We remove one of the red or the green, and you can see it just changes by 1 more. But if we delete both the red and the green initially, so that was our initial 2, was we put something here, we got a change of 4. The next change would just be 1. But if we instead make our change, instead of adding 1 in the middle, which was the biggest local change, we do, this is giving me all kinds of general things up here on the screen. Okay. If we remove both of these to get our change of 2 away, we now have 6 items that have changed as opposed to 5. So we can't quite do that. We were hoping that we would be able to do this greedy algorithm to go out and really find the best. But what we've shown is enough to give us smooth sensitivity, because we are able to bound how big this type of a change could be. And we're able to get this beta smooth upper bound on it. I'm not going to go into the math on this. It essentially follows from the original paper, except some adjustments made to how beta is divided to work a little better for this problem. And and then to bring down beta, because that's really your key, is bringing down beta gives you this steeper drop. And I'm not going to go into a lot of the details on the proof, but basically what we need to show is that we're getting this beta smooth upper bound. And using those bounds we previously showed on the change in sensitivity as we go farther away, we're able to demonstrate that. Leads us into a bunch of different cases. We work out each of these cases, and this gives us our bound on beta. So what does this mean? What this really means is that using this mechanism that essentially is based on what came out of the original paper, we can get down to an epsilon of 3 over 2t times log of 6. Yeah, we'd like to get smaller. But at the minimum, we can calculate what sort of a variance we get. So we're getting something where using simple global differential privacy, essentially sensitivity is off the charts. Using smooth sensitivity, something where we can at least show what we get in terms of the variance we see in the answers. Now, why is this interesting? What are the questions? How does this impact results? Well, it gives us higher variance than if we just ignored the missing data, but potentially reduces the bias. Now what we want is to help the policymakers determine, is this an appropriate mechanism to use? Should you, in this case, perhaps just say, do we ignore the missing data? Do we do something where we can provide epsilon differential privacy while doing the imputation? Well, it comes down to this bias variance trade-off. So, okay, I guess I was expecting a slide that's farther down. We're trying to empirically evaluate this. This is a little bit difficult because if we look at the data that's publicly available on this, or even not publicly available, what is your ground truth for missing data? The ground truth, you could say, well, let's look at the actual tables that have been generated, but those are generated from data that's been imputed using the current mechanism. So what we're trying to do is set something up based on the, we don't want to use the current ACS to do this because the values that come out of this are based on the existing allocation process. And you're right, not a kind of uniformly drawn random sample. There's all kinds of additional things that come in that make this comparison difficult. Our goal instead is to say, let's make a model based on this 1940 census data set where we presumably have reasonably complete data.
Can we grab the allocation flags?
Unfortunately, we really don't. We don't have the same type of allocation flags in that data. We've looked at those, and from what we can tell, they don't give us the same type of information as we have in the 2016 data. And the other problem is
All the missing data work in those data is modern. It's not from the 1940 census.
yeah,
It would have been done by IPMs.
yes.
I haven't investigated. You should talk to them.
Yeah. So that's yeah, and there's some other issues like the 1940 census data. I believe it wasn't originally machine readable format, and so there's little issues with how it got translated into that.
It was a major collaborative project.
Yes.
between IPMs and Ancestry.
Yes.
And all of that is modern methods,
Oh yes.
historical methods.
Yeah, and so there's a lot that went into that.
I'm just surprised that there aren't any allocation flags in the one that we poked up.
Yeah. Yeah. Well, that's something we looked for, and there are still some challenges in understanding exactly what some of that, because they have some other flags that are in there, but we don't see allocation flags that correspond to the types of allocations that are done with the modern or the recent data. But what we're doing instead is trying to model so that we can say, let's take the 1940 census data and generate a version that has missing data where it's missing in ways that are statistically similar to the way our current data has missing values. Because we know from allocation flags what is missing and been imputed in those data sets. If we can model that kind of missing, then we get something that's probably more useful because the way the data is collected today is different from the way it was collected in 1940. Even knowing how it was missing then is probably not a good model for how it's missing today. And we can at least treat this as a known ground truth. Again, at least the errors or where it's not true are not tied so much to the imputation method. And the hope is, our goal is to use this as a test bed so we can try to come up with a graph like this. Here's what you might expect the distribution to be if we were to use this allocation. Here's what you would expect it to be if you were to just ignore the missing data. The question is, does it look like that? Or does it look like this? Over here you might say, well, there's what I assume my true answer is, and yeah, maybe I'm better off taking something where I've done this imputation, even though my variance is higher, I'm still probably going to be closer to the true answer. Or maybe it's something like this, where, yeah, maybe you're actually likely to be closer to the true answer just accepting the bias and ignoring the missing data. We don't know what that's going to look like. And that's our hope, is that we can use this as an approach to say, here's what you would expect using different methods. Because that's one of the difficulties the ACS is putting in, is because they don't have the same sort of constraints and restrictions, but there's a lot of work that is done to get very accurate, unbiased results. And some of those things are very challenging to accomplish and still satisfy the privacy requirements. And we want to provide tools for people to evaluate those trade-offs, understand them, present them, make the decisions as to what are the appropriate methods to use. And some other challenges that we've been running into with trying to look at some of the research issues that come up in formal privacy for ACS. Well, the existing processes are well understood, or at least accepted, and so there is resistance to change, and so you want to explain what that change would mean. What is the cost of formal privacy under the current processing approach? Is it reasonable? If not, why? John needs to make changes to things and needs to push for changes. To be able to say, as he's done with the database reconstruction, look, we've got a problem. We can show you we have a problem. Are there, other than the database reconstruction, as he pointed out, this is not something we need to do again. But there are, there's other problems that come up, and so we want to be able to address those. What are the costs imposed by alternatives? You have various ways of achieving formal privacy. Which is the right one to use? How do you decide? in particular, we've been looking at things where we can say it looks like you have a bias variance trade-off. As you try to reduce bias, you're doing this in ways that require you to add more noise to satisfy formal privacy, and you get this trade-off. The stratified sampling that is used in collecting ACS data, this looks quite manageable. But some of the things they do in terms of waiting to conform to known ground truths, there are some real problems there where achieving formal privacy with what we know today, we're not certain how to do it. This is similar to the sort of constraint problems that Dan was talking about, but kind of on a different scale. And so our hope is that we'll be able to come up with some good arguments as to why some of these techniques that are really giving high sensitivity are actually not tractable to solve with while maintaining formal privacy, and that we should be developing new techniques that we can show will give both formal privacy and very good results. And so anyway, that's kind of what we've been working on. This is very preliminary results. I will point out we're in the process of trying to get some of the evaluation out the door so that we can get this written up as an interesting paper. I think just simply saying we can do smooth sensitivity for k nearest neighbor is, while it was challenging, it's not as exciting by itself as saying how does this actually impact a real world problem. And so we want to be able to say something about that. So, any questions before I let everybody head for lunch? You look like, John looks like he's ready to ask something.
Something else while you were talking.
Oh, okay.
This is a really good example of how a team can deep dive into the production function
Yeah.
for one of an agency's high-profile products, and notice that at each step of it, the challenge of applying formal privacy seems overwhelming. So I actually liked your conclusion, which is basically that you can't go in and try to re-engineer this so that each step is formally private. You get to steps like the missing data system, where what you're observing is algorithms that somebody understood eons ago as best practice being carried forward. No one touches them because they're in the production system, but they don't even approximate what you would do if you re-engineered the system. I think you must have basically found that every place you go. One piece of good news is those control weights at the end of the process that you were worried about, those will actually be differentially private over this next decade. So
Yes.
we can use composition there. When we're all
That
done,
helps us, yes.
things up even more by the controlling to the known totals. But I do think the right answer is, if you look at the output, what is it you're trying to, what's the information product you're trying to produce? And then you have all of these inputs, and then strip away the historical statistical processing of those inputs and evaluate the outputs for feasible, formally private methods. Some of the good things that were done historically can be preserved in there. Some of them are going to be swamped by the noise that the formal privacy gave, so you just give up on those, right? Yeah, that's an example.
And and I think the key thing is being able to answer that question as People done these things in some cases for very good reasons, in others for less good reasons. And where they're doing it for a good reason, how does this impact us? And as we come up with a new approach, whether it's to say, okay, here's a way where we can do this missing data imputation that accomplishes the same goals, but does so in a way that we can actually come up with something formally private, versus a simple mechanism of just ignoring it, versus some other approach that we haven't thought of, but somebody out here may think of that allows us to address this. How do we compare these in a way that someone can say, yes, this is what we want to use? And that's really our hope, is to be able to not just come up with ways to solve the problem, but ways that policymakers can answer that question. Yes.
So correct me if I'm wrong, certainly in the census, all of this processing, imputation, this is all going to happen before you end up with the disclosure policies. So is this still a problem if it's done, if you treat this as real data now and then you put that into the?
So the question is, as you push the place at which the privacy filter is placed deeper into the organization, what operations come under the control of the privacy loss budget? So the census operations that you heard the first two talks discuss, we made a very early policy decision that when the final version of the confidential data were delivered to the disclosure avoidance system, they would be treated as if those were the actual responses of each of those households. So that says that the privacy filter doesn't push into the organization. Now, that is an option with the American Community Survey, but as Chris's group has noted, it's not as simple for complex multi-stage probability samples and their associated estimates to say that the privacy filter is at the point at which you're computing those estimates. A, you don't compute them all at once, and B, some of the things you do to compute them are properly considered last step. They should be subjected to the privacy filter. So if you could push the privacy filter all the way back to the beginning, it applies from ingestion of the original survey responses, then this sequential composed approach that Chris's team was taking would be a viable alternative. But as he notes, there's so many places at which you have to infuse more noise than we know how to control at the moment, that the final output, when compared to other feasible alternatives, is not clearly better. It's the other feasible alternatives that are harder to develop, because they mean you're re-engineering a production system that already has its estimation and other assumptions built in. It was a huge thing to try to bite off in a single cooperative agreement, and
Yeah.
taught us about each of the stages.
Yeah, and I think the key thing is that so much of what is done basically increases sensitivity. Some cases by small tractable, or at least boundable amounts, but in other cases by amounts where there's essentially unbounded increase in sensitivity. I mean, we've run into some things where it's like, well, if we were to try to bound this, what can we do? Well, it turns out there's a hard implementation imposed limit because somebody used a particular field width, and that's the best we could do using the current process. Obviously that's not the way you want to go, but
How many times does the Census Bureau, in their policy, how many times do they reuse a donor? Do they have a policy issue on that?
So their current method is this hot deck imputation, which essentially once someone is a donor, they get removed from that list of potential donors for a period of time, and then they go back in. So
We don't do hot deck imputation at the Census Bureau, and we continue to call it hot deck imputation for historical reasons. We
Okay.
do cold deck imputation, except on surveys like the current population survey where the production time schedule doesn't permit having the entire survey in hand before you do it.
Yeah.
So they are actually started up with historical values in the imputation matrix and then populated with
So,
completed survey. But the ACS is cold deck.
okay, yeah, that's true.
All of the observations are available when the imputation mechanism starts.
Yeah.
And the census is also cold deck imputed by the standard definitions.
Now, that said, as was pointed out earlier, simply even saying you're never going to reuse a donor doesn't actually reduce your sensitivity from a global sensitivity point of view, even a local sensitivity point of view, because you get this strange problem of removing someone from the set of possible donors affects everyone after them. And so, how that first one occurs, how that first matching occurs, could potentially affect everything afterwards, because if you use this person now, you can't reuse them again. Well, if you had them to reuse again, maybe you'd use them here, which means you use somebody different here, and so forth. So that by itself doesn't change. One of the things to make this nearest neighbor approach work is to ensure that there was no such cascading possible. And there's some little tricks under the covers to make sure that happens that are kind of fairly trivial, not worth going into in detail. But that's one of the difficulties, is if you want to do this imputation, it really needs to be done in a way where it's not the fact, because it's not just the fact that you may be the donor in multiple cases that increases the sensitivity. It's the fact that a change in the database can cause a big change in the outcome of a query that causes the problem. And so again, like I say, what we may well come up with is saying this is something you don't want to do. That you get better results if you don't worry about this.
So I'm sorry to cut
So anyway,
the discussion
we'll talk
shorter,
later.
but we can take it offline if we want. And let's thank Chris again.